Okay. Good morning. Daniel, can you hear me?
Yep, I can hear you.
Okay, good. Are you recording? Yes. Yes. Well, I see that. So good morning, everybody. We have 12 people. It's 9 a.m. So we will start right now. And when people start arriving, they can pick up. So my name is Guillermo Avendano Franco. Okay. I'm admitting a few people. Okay. And I, together with Irene, Daniel, Jared, we will be offering this introduction to HPC as the main workshop, and two satellite workshops, one on Python, and another one, partial differential equations, computational fluid dynamics, software related to that area. So just to give you an overview of the expectations, the kind of topics that we will be covering right now. And these days, today, Friday, and Wednesday and Friday next week. Let's start describing a little bit what this is all about. So we will be offering a very introductory workshop on high performance computing, in particularly how to use our clusters. We have two main clusters that we operate, plus another cluster that is special, that is for HIPAA compliance, so for health science mainly. And that cluster is a little bit different, how you access that cluster and the kind of people that can use it and for which purposes that cluster is used. So we will be concentrated on just the two main clusters. In particular, our flagship cluster, HPC cluster, which is called Thorny-Flat. So everything that we will be doing today, Friday, even applying for both clusters, everything will be demonstrated on Thorny-Flat. So today we will be covering in the first part, in the first hour, very conceptual kind of lecture about the terminology, the terms that we use in supercomputing, in high performance computing, just to level the ground. And in the second part of today's lecture, we will be discussing the command line interface. Again, this is very simple. The command line interface is nothing specific for the HPC. It's just for those of you, which I imagine if you are entering to this topic for the first time, you are probably not familiar with the command line interface, terminals, that sort of thing. For the next day, so Friday, we will be covering terminal-based editors, so how you edit files, text files, from the terminal with an easy to use or a variety of options for editors, and which is a very important topic, how you access the scientific software that you need or you want to use in the cluster. So there are three main ways where you can access software: modules, conda environments, and singularity containers. So we will be discussing what this is all about. Collateral to this, in the afternoons, and the afternoon sessions are kind of detached from this. So if you want, you can attend the Python programming. If this is not interesting to you, you work on a different programming languages, R, or something else, and this is not of your interest, you will not losing any continuity with the topics on the morning. So if you want, in the afternoon, we will be exploring Python programming with a little bit of orientation toward scripting, not much into a big programming, more toward short, small programs and the basics of the language, those sort of things. For the next week, which is probably the most important sessions, we will be discussing the queue system. Let's learn how you submit jobs into the cluster, how you ask the cluster to do something for you, and how to use a terminal multiplex, which is a tool that is often used when you start working with HPC clusters for serious purposes. And in the last session, so Friday next week, we will be exploring a little bit tools related to machine learning, to deep learning, what we have on the clusters, and eventually we will be showing a little bit on examples on Dolly Sots, which is a cluster with GPUs, a lot of GPUs, which is more target for this kind of execution. And in the afternoons, Wednesday, Friday, next week, we will be discussing codes related. Irene will be discussing codes about partial differential equations, typical codes like Fluent for computational fluid dynamics, some other codes that solve the Einstein's equations, which is another way of another set of equations that are relatively similar to those that you use in fluids, but this time in the framework of general relativity. So some other codes that share some commonalities, and Irene will be discussing on those next week. So those are the plan for these 2 weeks. Again, this is very simple. The idea, if you see the structure of the lecture for each lesson, my idea is that you should understand, let's say, 80%, the first 80% of the lesson. At the end, I try to show you some tricks, some things a little bit more advanced. Eventually, some of you could be lost at this the final 20%. Or some others could find that interesting, and the first 80% will be boring or well-known or whatever. So I'm trying to balance that a little bit, but I expect at least to fully understand the big chunk, the 80%, which is very basic. So now let's discuss a little bit, and I will be reiterate on this in a minute, how you access the cluster. Still, you don't know the command line interface and all that, but still, I will show you how you get into the cluster. So if we have 2 clusters, Thorny Flat, which is a CPU mostly based general purpose HPC cluster. So we have like 170 compute nodes, so like computers. We will be talking about that in a minute, where you can run jobs. Each machine has like 40 cores, CPU cores. So we have like more than 6,000 processing units on that cluster for running execution, for doing calculations. And on the other side, we have a newer cluster called Dolly Sots, which is smaller. They only have like 38 compute nodes, but each node has a number of GPUs, graphic processing units, which are special devices that for certain kind of calculations, they perform extremely well. So like those in molecular dynamics, deep learning, some artificial intelligence more in general, they perform very well in those areas. So we have like more than 150 GPUs in this cluster, so it is specialized for that. So in general, you access a HPC cluster via two components, two pieces of software. One is a terminal emulator, and the other is an SSH client. Sometimes they come together, sometimes they are two different things, but integrated somehow, or you can use both. So depending on which operating system is in front of you, there are several ways of accessing or having the access to this couple of software packages. So I will be showing here briefly, and we will be doing this slowly so you can access, depending on the operating system that you have. In the worst case scenario, you are in Windows, which means that you don't have that software necessarily on your computer, but you can install it very easily. So if you go to this link here, you can download a software called PuTTY, which is one way of getting a terminal and SSH, a very basic SSH client, where you can follow the materials that we will be demonstrating in the second part, in the second hour today. Or you can use this other software called MobaXterm, which is, they have like a free version, and they have a portable version, so you can just download a zip file, you uncompress the zip file, you don't need to install anything. So if you don't want to use it, you don't want to installing things on your computer, you can just use it and discard it, and nothing will be installed in your computer. So that's another alternative. Just to show you a little bit how that looks like, if you go into the first option, PuTTY, this is how this looks like. And to connect to the cluster, you type here the address of the WVU's SSH gateway. So before entering to the cluster, you need to pass, if you are at home, you need to pass first through a special machine that kind of provides some security behind. And you first connect to this machine, and after you can connect to Dolly or Tor. This is how you use that. It looks like this. Here is my username. In your case, you will have to type your username. It will ask for your password, and after it will ask for your Duo authentication, and you get into the gateway, and from there you jump into the cluster. We will be showing this in a minute, at least on my computer. So I'm sitting on a Mac, so but it will look very, very similar. So this is how you jump into the SSH gateway, and from there you just go to the specific cluster that you. So here I have the instructions. By the way, I will be actually typing this, so you can get. Okay, thank you, Daniel. That's the page. You can follow that page. You can follow the instructions there. So yes, thank you. Let me see. Okay, and if you choose the other option, MobaXterm, it offers a more graphic with more capabilities, if you like. You just go well, you type here ssh.wvu as shown below, and you basically get the same access. The advantage of MobaXterm is that not only it offers you the SSH connection, but also you can open Windows from the Unix Windows from the remote machine into your computer. So you can eventually see a plot or something. Sometimes that could be handy. Otherwise, both software packages will serve the purpose. No problem. Now, this is if you are in Windows. There are some other options that I think I described, like using, probably have that thing here. Oh, probably, yeah. If you want, there are some other options. You can use Visual Studio Code. This is another alternative. There is something called the JIT desktop, which is also comes with an SSH client and terminal. You can also install a Linux, like a Linux system inside Windows, and from there you have all the commands that you will learn in a minute, in an hour or something, and that offers you another way to jump into the cluster. Or you can have PowerShell and use PowerShell to jump into the cluster. There are many ways. So now, another alternative is if you are on a Mac. If you are on a Mac, the terminal is there. The terminal is under utilities. Let me see. Yeah, there is something called utilities, and inside utilities, there is a terminal. So you can use that. It will be something like this. And from there, you just type SSH. In that terminal, you type SSH, your username, which is something that is unique for you, or the username that you use for the email, for accessing the cluster, for many things inside campus, at ssh.wvu.edu. So that will logging you into the SSH gateway, and from there you can jump into the specific cluster. So this is very simple. If you are in a Linux machine, it's also very simple. The terminal is so central to Linux in general that you have it somewhere, probably in front of your screen on a desktop bar or something. You have a terminal, you click there, you open terminal, and you type SSH space your username at SSH.wvu. That's another option. And final option, regardless of which operating system you have, you can also access the cluster via Open on Demand. Open on Demand is a web interface for the cluster. We have that interface here for Thorny and for Dolly. So when you go into this link here, you will land in something like this. After authentication, after you enter the password and Duo and all that, you will land inside your web browser, regardless of the operating system that you have. In your browser, you will see something like this. And from here, you can open a terminal into the cluster, and you can start typing the commands that we will be learning in a minute. And we have another, the equivalent to that, for the dolly slots. So the difference is that here we have on-demand-ds, and here we have on-demand-df. So I will actually copy this here on the chat. So something like this. Okay, all those options at the end will give you access to the cluster. Let me see here. So regardless of which method you use, you will be ready to access the cluster. Now, the more generic instructions here for the clusters are: first, go into the SSH gateway. So SSH username at ssh.wvu. And from there, once you log into the cluster, you will be typing either this for connecting to the Thorny Flat, or this to connect to Dolly Cells. So allow me to demonstrate that here. Let me see. Okay. So this is my computer. And I will be logging into the Thorny Flat. I will follow the same procedure. So I type SSH. This is my username. It will be different for you. .wvu.edu. So it will answer, okay, enter the password. I will be typing the password, and after the duo, I will select one of my cell phones, and it will be clicking here. Let me see. And I authenticate with duo, and I land on another computer, the SSH gateway. You notice that you are on a different computer because of this name. We will be discussing this in a minute, the command line interface and how but the important thing is you will see this. When you see this, you know that you are in one of the WVU SSH gateways that the university provides to its users. And from there, you can jump into the cluster. So to do that, for example, I type HPC, hpc.wvu.edu for Thorny Flat. So I type that, and now I am in Thorny. This is the name of the machine. The name of the machine changes from this WVUSSH something into this TRC. This is the login node. We will explain all that in a minute of the HPC cluster. And from here, you can start following the tutorials, the examples, everything that we will be doing in the second part of this. So now, let's move into the first section, which is relatively passive. Let's just change this to the actual lecture. So this is for the actual, let me put this, for the actual lessons are here. And if you want everything that I discussed before is here described. So the SSH, how you type that, how you access Thorny and Dolly and all that. Same thing. So you can follow here from this website that contains the lessons. The real material is right here. So now we will start discussing the concept. This is a more conceptual lecture. We will see how much time I will take for this. The idea is for you to have a language, common terms, a very precise language for what we mean by storage nodes, compute nodes, RAM, CPU cores, all that terminology related to computing, to high performance computing, how having some precision of the language, so in the future you know what we are talking about when we say, okay, you execute on one node or two nodes or something like that. Okay. The first thing to know is that we are doing calculations every day. Some calculations are very simple, as just, for example, sums. If you want to compute, you are planning to buy a few books and you are deciding if you have a certain amount of money on your pocket, you can take the books and start making a sum to see if you buy this three or just this two or something. You are doing sums. You can do that out of your head, or every single smartphone today, they have a calculator, and so you will be doing using the calculator. That's one thing. But calculators are good up to a certain point. or your head, it's good up to a certain point. And for certain calculations, your brain is not enough, and a normal calculator, a physical calculator, is not good enough. So you move to something else. For example, if you are computing how much you will be paying for a loan or mortgage, you probably go and do that with a spreadsheet. You will be deciding, okay, how much you will be paying, doing um, composing the rates, computing all that. Or you use a program on the web that do those sort of calculations, compute the amount you pay for the principal for the interest rates, all that. So you use something else. There are some other problems where this kind of approach reach some limits. You can do wonderful things with a spreadsheet, and you can make plots, you can compute many things with that. But sometimes that tool is not enough. So you need something bigger. At that moment, you can try to build a program or use a program that will do something. For example, you have a big data set with millions of rows and tens of columns. So if you have millions of rows, you cannot use Excel, you cannot use a spreadsheet for that, simply because there are limitations. In Excel, you cannot have more than 1 million rows. So you can simply not use that. So you use something else. You use Python, for example. We will be showing that a little bit in the afternoons. Or you use a program that is specialized on crunching the numbers of big data sets. Or you are doing a simulation. You know certain parameters of the physical, you have a model for that, and you have programs that with those inputs are able to process the evolution of a set of atoms, molecules, stars, fluids, whatever. And those calculations are very expensive computationally. It will take hours to do that. So if it's not too big, if you are just working in 2 dimensions, maybe your computer is okay. Computers today are very powerful and can do wonderful things in a few minutes. But there are cases where you want to do a real simulation in 3D, the system is big, you are trying to simulate the behavior of fluids in a motor, or big molecules, biological proteins, layers, things like that. So a normal computer is not good enough. At that moment, you move one step higher, and we are entering the real supercomputer. So supercomputer is one area of machines that are specialized in crunching big amounts of data or large numerical processing or text processing. One prototypical case back in the 90s. So there are basically two kinds of supercomputers. One, those that are built from the bottom up to be a supercomputer. This is just one machine with a lot of electronics, very specialized for crunching numbers of a certain kind of problems. Those are one kind of supercomputers. Very typical cases for prototypical case are those Cray machines from the late 70s, 80s. So those are big machines, very beautiful, well designed. Doesn't resemble a computer at all. It's just like a furniture, basically, with a lot of electronics inside, for doing a certain kind of calculations. Some other computers back in the 90s were trying to say, well, what if I take a few computers, normal computers, I attach those computers together with networks, and I use them to compute something. That will be getting like a supercomputer with more common commodity hardware. So all computers, for example, you collect the computers in your college or your department, and from there you build a supercomputer. Those are called the BeWolf superclusters or BeWolf supercomputers. And that trend kind of are grandparents of one big chunk of what today's supercomputers, which are the HPC clusters. The HPC clusters are one specific kind of supercomputer that is built from an aggregation of relatively normal computers, something that resembles a computer, that looks like a computer, something that you can attach a mouse, a keyboard to it, and eventually you can work with it. And we will see that in a minute. With another thing to know is that in the realm of high-performance computing, everything is, the main concepts for that are size and speed. And those machines together are much faster than a normal computer, an individual computer. And sometimes individually, each computer from the HPC cluster is far more powerful than a normal computer, a regular desktop or laptop, or even a workstation. That's one thing. And also size, both the physical size of those machines, which is like, could be fill a room or something, or the internal size, the amount of storage, the amount of memory, the number of processors. Those machines usually are much bigger in capacity, in processing capabilities than a normal computer. Okay, so now let's discuss a little bit the anatomy of an HPC cluster. And this is just a very cartoonish description of an HPC cluster, more like a BeWolf cluster. You see a few towers here. In reality, they are no longer towers, and many people don't even recognize this as a computer, except if you are a gamer. Most people sit in front of a tablet or notebook or laptop computer or something. So these towers are probably not the most representative icon for a new generation. But if you are a gamer, you recognize the tower. You see, okay, that looks like it's not so shiny and with lights inside, but this is a computer. They say, okay, this is a computer. So a cluster is all this, except for this little guy here, which is you sitting in front of your old computer. The computer is no longer like this, but this is like an old computer. This is your home. Everything else here is a representation, a cartoonish representation of an HPC cluster. You have nodes. You see nodes, and this is another node. Those nodes are the machines that constitute the cluster. There are basically two sets of nodes. Those here that you see, like 8 towers here. Those are the compute nodes. Those are the machines, those are computers that are actually in charge of processing the jobs of everybody that has access to this cluster. Could be hundreds of users, could be thousands of users. So in our case, we have like 200, more than 200 users. And on a typical day, we have 30, 40 users connected to the cluster, doing simulations, doing calculations on those machines. So these 8 compute nodes, in our case, are like 170 computers. Okay, there is another set of machines that are called infrastructure nodes. One of them, for example, is the login node. It's represented here. It's the machine that you connect after you jump into the SSH client. From there, you jump into the login node. The machine that I show you, oh, let me see. this description here. So you see here the compute nodes, you see here the login node, and you see here another infrastructure. Those computers here are in charge of very specific tasks. They are not meant to run any calculations for you. They are just for serving the access to the users, managing the storage, which, by the way, usually the storage is separated from the computers. So the computers see your files, your folders, all that, but the physical location of where that data is a separate device. It's a separate machine that is represented here with those orange cylinders. That could be hard drives, SSD drives, those sort of things. Okay. So this is a representation of like old-fashioned representation on HPC cluster. Important concept here, there are compute nodes, infrastructure nodes. You should compute, or you do your simulations on the compute nodes, and you can connect to the machine to a login node, and from there you submit jobs. We will see how that works. Okay. To get an idea about the specifications of an HPC cluster versus the specifications of your computer, and get an idea of the scale of that, I am proposing here very quickly that you take a few seconds while I'm describing this to compare the specifications of your own computer, and I will show you the specifications of the login node, which is a representative version of one of the compute nodes in the cluster. So depending on which operating system you have in front of you, there are several ways of checking a few numbers, a few specs of computer. So here I'm showing you, if you are using a Windows machine, you can go into the control panel system here and check a few things. So here you will see the kind of processor you have, the amount of RAM installed, but this is an old computer, so you have a normal, regular computer today. 4 gigabytes is probably the bare minimum. You probably have 8 gigabytes of RAM. This is a special kind of memory, and you probably have a much better, much newer processor, something, an Intel processor or AMD processor or something else. Here, okay, that's for a Windows machine. If you are on a Mac, you have something like this. You can go and click on the Apple in the top left corner. And this again is a relatively old machine from 2013, so now more than 10 years old. And you see the processor, the amount of memory, and eventually if you move it here and click into storage, you will know how big is your hard drive. Usually those machines, laptop computers, they have SSD drives, so solid state drives. There is nothing mechanical moving into it. But eventually, if you are on a desktop computer, you probably have a combination of hard drives, mechanical hard drives, and a few SSD drives for performance purposes. And if you are on a Linux machine, it depends on the specific distribution of Linux you are using. In the case, for example, of Ubuntu, you can see here the processor, the amount of RAM. If you are on a Linux Mint machine, you can see something like that this way. Here you have like a more detailed description about the processor, the memory, the graphic card, all that. by the way. So try to use that, and I will compare that with the kind of information that I will be showing you here. Let me see if I can make this bigger for me. Okay. So this is probably oh, okay. So I will have to log in again. So this is the login node of Thorniflat. And this is the configuration of this machine is very similar to the configuration of the entire cluster, relatively similar. So I will be checking a little bit with a few commands. If you are here, you can type those commands. You will be learning about those later. The specifications of the processor, for example. You can type this, and you can see this machine is a Intel Xeon Gold with this speed. We will be discussing that. There are a few things here, a few cache memories, some other details that we will be discussing. So you see here the kind of processor and the speed of this machine. There is also this command here, well, where you can see the amount of memory on this machine. So in Thorniflat, the minimum amount of memory that we have is around 96 gigabytes of RAM. This most probably will exceed what you have in front of you on your computer. The regular computer will have 16, 8, 16, probably 32. In a very rare occasions, maybe you max out the machine, the memory of the machine, and you grow the machine with 64 gigabytes of RAM. But it's very unlikely that you have more than that. Except if you have a workstation or something where you decided to use 128 gigabytes of RAM. But 96 is a big jump from what most likely you have in front of you on your computer. So that's the memory, that's the processor, and here you can see a little bit the storage. We have several locations for storage, but I will be concentrated for you to look into these numbers. The machine is connected to a storage of 760 terabytes of for the home users, for the system itself. So it's close to a 1 petabyte of data, but it's split in two entities, two separate file systems. But that's basically what we have, closer to 1 petabyte of data, from which we are using roughly 90% on each of those file systems. So that is in a quick overview of what we have. And from that, you can compare with your own computer. The processor, the speed of the processor, the amount of RAM, and the storage that you have. And eventually graph processing units or some other things. So that leads me to try to explain a little bit the advantage of using an HPC cluster. So first, the speed. Those machines are much faster in general. With some exceptions, are much faster than a normal computer, except if you have a very, very recent laptop that could be eventually faster. Those machines are an aggregated computer, so you can use multiple compute nodes on a single problem and they can work together if you have software that is capable of doing so. They put several machines to work together. It's more efficient than a normal computer and regular computer, thanks that you have a pool of resources, the biggest storage, those things are connected in special rooms where the temperature is controlled, so those machines try to avoid overheating, a set of things that make them more efficient in general. The bulk cost is lower. Those machines are meant to be used by many people all the time, 24/7, as much as possible. So overall, you are using the resources in a better way, and they are convenient. All the software is there that you want to use. And those machines are periodically updated to a certain point. So there are several advantages on using them. So now let's describe a little bit internally what happens with every of those, what is inside those compute nodes. A little bit of terminology on that. So the compute nodes. The compute node is a normal computer. So it probably doesn't look like a computer because those are meant to be stuck in racks like refrigerators, kind of that. So a big metal chunk where you can stack computers on top of computers. You can stack 20, 40 computers on one rack. But internally, they are regular computers. So they have CPUs like those. You see this is like the CPU of one of the compute nodes on Thorney, Xeon, Intel Xeon, that is the chip. And on top of that chip, you have a big metal zinc, eventually with some fan to dissipate the heat. This is the device that produces most of the heat of that machine, and they consume a lot of energy, convert that energy into heat. In general, there are two main brands for CPUs commercially available, at least here, AMD and Intel. So depending on the cluster, on Thorney, we are entirely Intel based. On Dolly, we have a mixture, but it's basically AMD processors. Inside this chip, we have what we call CPU cores. Those are processing units that are capable of doing everything like additions, multiplications. They crunch data. And the way modern computers perform better is by integrating more and more cores. So in the case of Thorney, our processors, they have, for the most part on Thorney, 40 cores on each processor like this. It's this chip. Inside this chip, 40 replicas of a processing unit, and all those 40 replicas are capable of processing the data inside. We have a few machines with, so in reality, what we have is two chips like this. On each compute node, we have two chips like this, and each chip has 20 cores. So in total, they have 40 cores. And in some machines, we have 12 plus 12. So two processors, two chips, each with 12 cores. And those are the machines with GPUs. So they are slightly different. So that is the idea of cores. So cores are entities that are inside the CPU. there is one concept that is often mentioned for consumer products, the hyperthread. So they mention that your processor is capable of hyperthreading, so it looks like a core machine, even if they have only 4 cores. So they look like a 16-core machine. Well, actually has only 8 cores. So that is a way for the hardware to optimize certain processing, especially for consumer applications, or eventually for some server applications, like those in the web servers, database servers, things like that. We usually disable all that. We disable the hyperthreading because in real world scenarios for crunching numbers, for doing real high performance computing, they do not offer much advantage. So when we say that we have 40 cores, we really have 40 cores. It's not that we have 20 and we are doubling that with hyperthread. No, we have 2 CPUs, 2 chips, and each of those chips, they have 20 cores. So in total, we have 40 cores for processing, the real 40 cores. That's one thing. CPU frequency, that is the speed of the processor. For almost 20 years, the speed of the processor have been kept constant. There are not much hope of raising the speed as we used to have to raise that back in the 90s. You're probably younger, but back in the 90s, mid-90s, you have a machine with 200 megahertz. 2 years later, you have a machine with 400 megahertz, and after 800 megahertz, and after the first machine with 1 gigahertz. So every 2 years, the manufacturers were doubling the speed of the processor. And that was the way of offering to the customers a faster and faster and faster processor. We can no longer do that, because if we raise that from 2 gigahertz to 4 gigahertz, those processors will produce so much heat that will probably risk melting the chip itself. There are not ways to dissipate that heat efficiently with just normal air and a sink on all that fast enough. So either you put that machine inside liquid nitrogen and try to cool that somehow with a very expensive device or something, or liquid cooling, which is also expensive. There are ways of dissipating heat in a non-traditional way, so not just with air, but those ways are expensive. Nobody has at home its own pool of liquid nitrogen to cool the device. So the solution is not raising anymore the speed. You will see that the processors that you have on your computer, they are probably 2 gigahertz, 2.6, maybe 3, no more than that, but they will oscillate closer to 2 gigahertz. Instead, as we cannot raise the speed that way, what we do is to put more cores. So we are replacing that speed for having more cores and eventually a bigger area on the chip. So we have better ways to dissipate that, thanks to the area of the chip. So that's one thing. Now, cache. Inside the chip, they have a special memory that is called the cache, which is responsible for a big chunk of the price of the chip. So low specs, so the processors that you see for consumers, for cheap computers, like Core i3 and eventually Core i5, Core i7, all those things, the basic difference is not the speed of the chip. It's usually the size of the cache and eventually some extra instructions. So extra niceties that make them perform better as you climb from i3 to i5 to i5 to i7 on the AMD, the rising different generations of that. And one important metric is the size of the cache. This is a very fast memory that is really, really close to the processing, the chips that are crunching the data, that are processing all the instructions. So the bigger this memory is, the better is for the processor to receive, to feed the processing units with data to crunch. Otherwise, some of those cycles in the processor will be lost just because it's waiting for data to arrive from the hard drive or the memory, which is relatively small compared with the speed of the internal processor, and that is killing the performance of the machine. So usually you see in the machines that we have in the cluster, very, very fast, large cache, multiple levels of cache. So one cache could be 24 megabytes. Doesn't look big, but this is a very, very extremely fast memory, and there are lower levels. So cache level 2, cache level 1, that are in charge of keeping the processing units with data so they don't lose time just waiting for that. So that's another thing to look into that. If you want you can see all the specifications of your processor. If you are using Intel or AMD, you can go into these links here and check your specific processor, the cache levels, the speed. Some of them offer like a boosting speed. That means that a machine with 20 cores, eventually they can disable some of those cores to raise the speed on some other cores for certain calculations or certain processing that is very serial, so you gain an advantage by balancing numbers of cores by speed. So manufacturers make all sort of tricks to increase the performance of those devices. Storage, again, on Thorny Flat, we have a storage system separated with around 1 petabyte. And that is considerably bigger with probably what you have. You could have 2 terabytes, 8 terabytes, eventually 12 or 16 terabytes on some computers, but roughly you are on that that realm, and that's pretty much okay for a normal computer, for a regular computer, storing music, videos, all your data, all that is okay. Now, the network on those computers is also different. You probably are connected. I'm connected using Wi-Fi. It's okay for watching a video, making a call or something, but that is not enough for processing data. When you are communicating between computers, they are sharing huge amount of data, and you need to share that amount of really, really fast. We use very special networks for that are very, very expensive, and they are, again, a big chunk of the price of the machine per node. And what you pay for that is low latency. So the amount of time that it takes to move the first bits of data from one machine to another, and the amount of data that you can move like a highway between one computer and another is really, really big. High bandwidth, low latency, those are concepts that are important in those networks. And the typical networks, Ethernet, the networks that you have with cables at home, they could have some good bandwidth, but they don't have good latency. So they are relatively small, and they are not good for computing in parallel. So multiple machines computed at the same time, they are not good. So finally, let me describe a little bit some extra elements. This is a photo of Thorny Flat. We have two clusters here. So this is how those machines looked like in reality. Thorny Flat is located at Pittsburgh Supercomputer Center. And it looks like this. Those are towers, racks called racks. So here we have like 20 machines. On the next rack, we have another 20 machines or 40. And we own like 4, 5 racks where we have the 170 something machines for Thornton. So 178 compute nodes, more than 6,000 CPU cores, and 47 GPU cards. So that's Thornton. Dolly Sots is a different cluster. It's smaller. You see here all those, you see here some red dots here, some red and green dots. So those are the half of the machines of Dolly are here. The others are on a row behind that, so it's not visible from here. And there are a few machines here, so on the big nodes that you see with the 4 fans out. And on top of them, they are the infrastructure node. So this is how a cluster looks like. A bunch of computers, they doesn't resemble normal computers, but they are actually computers that they have their own processors, memory, and network capabilities, all that. So those. And on the left side, those are machines for cooling the room, for powering the rooms. You see here on top, like the plugs, how you connect, they give power to those machines. They were big power units. So this machine, it's at Tyrrell, the chemistry research lab, the building downtown. This is where the machine, on the second floor, this is where the machine is located. So this is Dolly Sat. So you have here a little bit the specification of Dolly and Thorny. And with this, we close the concept part of the concept that we need to learn about high performance computing. In your due time, you can go into the web page and oh, I see a question here. Do the names, which names? The names of the cluster? The names of the cluster, when you say, if that is the question, are related to some geographical significant places around West Virginia. So Thorny Flat is one, and Dolly Sots. There are like mountains. There are places in West Virginia. And our very first cluster, it's from 2011. So the first time that we have like a big cluster. That cluster was called Mountaineer. That was in 2011. And after 2013, we have another cluster called Spruce Knob. And after this, now we have Thorny Flat, Dolly Sots, and then newer cluster that will arrive beginning of next year is Harper's Ferry. This is another like a 1.5 million cluster that we will be purchasing in the next few months. So by the way, those clusters are like that. So a modest cluster is around $1 million. On top of that, big infrastructure like those in Pittsburgh Supercomputer Center, they are one order of magnitude higher. So those are machines for $10 million, $20 million. And the biggest clusters in the US, in China, Europe, the flagships for a country, those machines are well on top of the $100 million. So those are very, very expensive machines. The maintenance of those machines is expensive. They consume, so those clusters could consume easily the same amount of power or very similar amount of power as the entire Morgantown. So one power plant just dedicated to one data center for those HPC clusters. And they have very, very special ways of cooling those. They are big. They could be as big as like a Coliseum, something like that. So that is like an idea how you scale that. So just to close this a little bit, well, we will be talking about the command line interface in a minute. We will be jumping into that. And so I will be skipping this discussion. This is another description of the internet, how you use SSH, as I described in the first part, to the login node. And from the login node, you submit jobs that will be executed by the compute nodes, and those nodes could eventually work together thanks to a very high speed network like InfiniBand, Omnipad, or some different technologies that allowed computers to send data, communicate data really, really fast, low latency, high bandwidth. So here I have a few exercises. You can do that. We will be stopping, I think, around 10:30 for 50 minutes for you to relax a little bit. And after, I don't know exactly where I will be at that moment in the command line interface, and we will continue for the rest of the hour to noon with the command line interface. So now, go to thoroughly and execute these commands as I did a few minutes ago to know the processor, the memory, all that, so and compare. So now getting the big picture here, the biggest clusters on Earth. I'm not really sure if this is still outdated, probably not. There is one site that is called the top500.org, where they kept records of the publicly known faster supercomputers on the planet. When I did this last year, and so these numbers could have changed a little bit, the number one computer on the planet was Frontier, that is at Oak Ridge National Laboratory, and the number 5 was because probably that had changed, and now it was Summit. And on the Chinese side, they have Tianhe 2 and some way Tianhu Light. I'm pronouncing that wrong. So just to give you an idea, the biggest clusters are both in the US, China, eventually Japan, on a certain distance, Europe somehow. So you see, having these machines and using these machines is very critical for keeping certain research that are very computationally demanding. So countries expend a lot of money on having these kind of machines. And now today, with the geopolitical climate, China have decided to lower the profile. So some of those machines, people know that exist, but they are not announcing the performance figures for those machines, so they don't raise as much in those listings, but by indirect ways, people know that China is on par to the US, on probably, and now a little bit higher in terms of the power of those machines and the total number of big first-line supercomputers on the planet. From the other side, high-performance computer is one of the areas that is very, very important for scientific development. If last year there was a publication from a think tank that produced a list of the biggest or most relevant technologies for today's research. And from those 44, they produced like a list of 44 technologies. And at that moment, last year, China was leading in 37 of those. The good news is that the US is still leads in a few of them. And high-performance computing is one of those technologies where apparently is still on the lead for high-performance computing. So that is here you can see the report, the link to that report from this think tank or research institute. So high-performance computing is something that is very important, especially for these highly developed countries, for certain calculations, certain simulations in all areas, atmospheric, climate change, nuclear reactors and nuclear weapons, simulations, all those things, astronomical, astrophysical simulations, material science, all that, they use supercomputers. And there is a need for having very, very powerful supercomputers. So there is a competition there too. So now we will be moving in the next 15 minutes, like try to move this on the command line interface. So for a new generation, this is probably really, really new to you. Back in the 90s, it was not that unusual. So I am from the 90s, basically. So that was like college level. So I started working with computers for scientific purposes. So we have computers with terminals. So that was relatively normal at that time. Yes, at that for around the same time, we have the very first versions of Mac, the Apple operating system, and the Windows 3.1, Windows 95, and they were with icons and very graphical. But still, for scientific purposes, when you went to university, they have mainframes, servers, and you work with a terminal command line interface. But not today. Today, you are used to your cell phone, a tablet. Everything is very, very graphical and very touchy. You just touch your fingers here and there, and things. So this is probably unusual for many of you to deal with the command line interface. So that's why I will be trying to move into this relatively slowly, because I know this is natural for me, but could be not so natural to you. So if you have a question, just type your question. If I'm making something that is not clear, it's because I'm not making it clear enough because of me, because it was natural to me to work that way, but not necessarily to you. So as I told you, today we have cell phones, screens, eventually with touch screens, tablets. So your interaction with computers is via a mouse, a pad, or keyboards, sometimes with the voice. So computer recognize your voice and will start doing things when you ask them to do so. But to use an HPC cluster, we rely for the most part on a terminal and the command line interface. Has been like that for decades and continue to be like that. And so it is important for you to learn the command line interface, the commands, and all that. So I showed you before how you connect to the cluster. And once you are on the cluster, let me see if I can this really quickly. Let's see. Probably my terminal is now dead. Yeah. So I will be doing something now. So as this, oh no, wait a minute. Let's see here. I'll be sharing here, and I will be creating a new terminal. And I will show you how this looks like, because I will plan to use. So here I will be connecting once again to the cluster. But I will be doing something else. Okay. So with this, my terminal will survive. Later, I will show you about the terminal multiplexer, the kind of things that I did quickly here for demonstration. But I will be jumping for a moment here. So you will see before I do that. So you see here that I'm on a terminal and I can start typing commands. This is what we will be learning right now. And you will have the opportunity to do that in a few minutes. We will stop probably in 50 minutes, like half an hour around. I will see a good point to stop. So you will have the opportunity to test a little bit this, and in 15 minutes we return and continue. So you will be using what is called the shell. So the shell uses the idea of ripple. So you type a command, the machine will understand that command, will do something about that, will process that, and will probably print something on the screen and return you to the prompt, what is called the prompt, that looks like this, looks like a dollar sign, or sometimes like a dollar and bigger than, something that give you the idea, okay, I'm ready to receive another command from you. And you interact with the computer one step at a time. You type a command, the command is executed, something happens, it returns back the prompt, and you type another command. This is how most of the people using HPC cluster work, except for those who will be using the web interface. It's something that if I have time, I will demonstrate today or next session. But that's how you use that. The advantage of that is it looks dummy to just work one step at a time and waiting for the program to do something, while on your desktop computer you can be reading here something on the news, reading email here, eventually listening to music, changing something, a video here. So on a desktop regular computer, you are multitasking more. You as a human are doing several things at once, and you change from one window to another. But this is different. So you execute one command and you wait and you execute. There are several advantages of this. One is automation. So imagine that you are editing an image or something, and you are doing something. So you go, you know, okay, I'm editing an image, so I will be opening a program for image editing I will be adding like a name or the date on a corner of the image, doing something, saving the image. Now, what about if you need to do that for 10,000 images, 1,000 images, more than that? You will not be doing that one by one, opening the image with the program, editing the image, saving that. You will be using a script. You will be trying to automate that. The shell put you one step closer to that sort of automation. If you are using the right tools, you could eventually editing figures massively, or the figure will receive the text in the right place and saving the figure, and you can process thousands of figures in a few seconds with the right commands, with a script. This is one of the reasons why you use the shell. The shell is in itself a programming language that you can use to automate execution. Now, for us, we have some materials here for these lessons. So this is a good opportunity to execute this command here on the terminal. If I will put this here, let me see, you can put it here. And okay, you have to type it as it is, so just copy and paste. Once you log into Thorny, execute that, it will download all the materials for the lesson, for the session. And now you will, at the end of this, you will have a folder. And I will see, let me see if we can do this. Like this. Let me see. Okay, so with this, let me see if I can. So I did it. So I have this, let me see. I will be filling that. And I will be cloning all. So this is the command that I expect you to execute. And it will be downloading all the materials for the lessons today. So, so you see here that you can execute commands. I ask you to just trust me, execute this. Later, we will explain about that if we have time. And after, I ask you to execute this. And now I will be showing you a little bit the description, and later you can execute that. So the idea is that by typing those commands, you know which command where you need to execute. You can move across the file system, you change directories, you copy files, you remove files, you delete, you edit files. Later you will learn about that. We will be doing all the kind of things that people do every day on an HPC cluster from the command line interface, just typing commands. This is hard for the beginners, so I'm going slow with this, and I'm trying to have patience with this. So one first command that we execute is ls. If you execute this, once you are executed this, once you download it, you will download the materials, you change directory into this workshops hands-on, and you execute ls, you will see something like this. Let me see if I can do it here. Yes, so you will see something like this. In my case, it's colored, so you know, I know which things are files and which things are folders or directories. And there is another command here that is shown like this, where you see more explicitly for those who are running this on a terminal not capable of coloring, which is unusual today. and a slash at the end of some of those entities that allow you to differentiate files from folders. Now, yeah, okay, yes. So commands could have arguments, as I showed you a minute ago. So you can type something like this. ls is a command for listing the contents of a certain location on the structure of the file system, the files, folders, all that there. And with this extra argument, we are changing the behavior of the command. The command is a program that can execute things that were programmed to execute something, to do something, to show you something. And here there is another option, ls minus l. I will show you here, ls minus l. So it show you a different view of the files present inside that folder, the folder for the workshop. So you see here, like a library share. Those are the permissions, the owners, the sizes, dates, a few things about those files and folders. And that's how you navigate into this system. If you don't know, you know the command, which is unusual. This is a little bit counterintuitive, but if you know the command, and at the very beginning you don't know the command, but imagine that you know the command, you know that it's ls, but you want to do something, but you don't know exactly what to do with that. There is a manual with the man ls, which on this case I don't have a manual here. Oh, okay. I was thinking that I have a manual. Let me see. Maybe one. Maybe I have it here. The manual for that. Okay. Right. I didn't have it on Thorny, but on Dolly, it will look like this. Sometimes the manuals are installed, some other times they are not installed. But so that's how this looks like. You can see all the commands, all the options, arguments, and what they do. So, and you live from this program, from the manual, with the letter Q. This is, wait a minute. Where do I have that? Okay. 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 So this is how you access the manual page of that. Those manual pages are also online. If you want, browse Google, use Google, and you can search the manual for a certain command and all that. Now, the structure of the Unix Linux file system. On a Unix, Linux, Mac OS, so all the operating systems that as an heritage from the original Unix systems, they have a structure that looks like this. It's like a tree of roots going down. So it's like a tree upside down. So you have the root folder, which is the slash. Below that, we have a certain number of folders that are relatively standard. So all Linux, Unix systems, they have pretty much the same folders in the same place with small variations. Even a Mac has something like this. And one of them, in the case of Thornyflat and Dolly Salts, there is one folder, for example, called users. Inside that folder called user, we have all the folders for all the users in the system. I am one of the users, so I have my username is one of those folders. And inside that folder, as I download the workshop materials, I have a folder called workshop. And inside that workshop, I have the introduction to HPC, the materials for the parallel computing workshop, for some other workshops that we offer, and a README and license file. So we have that. So you see, and now I will be going into using the CD command to move to the different folders. You see all the users in the system. We have many users. Now I can go to Gianfranco and I can go to the workshop and so on. And you will see here the license, the README, the introduction, HPC. That is the structure of files and folders inside a Unix or Linux file system. That's one thing. Another, there is one command I see that give you also a very more graphical view of the structure of that. And let me see if I can show you this. This contains all the files inside workshops and so on, all the files that we have there. So with the 3 commands, you have a view of that. Otherwise, what you have is ls cd, you start changing and navigating across the folders. So again, slash is the root folder. From there is a folder users, and inside there is a folder with your username and all your files that are there. So as a quick note, on macOS is the same thing. On Windows it's slightly different because the drives are identified with letters. And when you move to a different drive, an external drive or something, they are identified with a different letter. So it's slightly different. And the way you describe the folders instead of being a slash is in the backslash. So there are some similarities, but Windows is probably the most different from those operating systems in the way it looks into the structure of files and folders. Now, a location in the structure is called a path. And you can see the path with the command pwd. So that is my location, my current location in the structure is /users/Gianfranco/workshops and so on. That is my current path. And the command pwd, this is the second command that we are learning, we can know where we are in the file system. From there, you can see introduction to HPC or some of the folders. You can navigate into them. And if you execute just the command cd, you will be going back to your home folder. This is called, there are several ways to call the home folder. This is one, the curly tilde is a shortcut to the home folder, or the variable home is another way of moving into that. So all those were ways of moving that. We will describe that in a minute. So from there, you can list, for example, use the command ls to list the contents of a folder. If you describe that, for example, with the curly tilde, workshops and introduction to HPC, you can see or you can list the folders and files inside introduction HPC. There are several alternatives to that, but in general, those are the ways you jump between those folders. So as an exercise, and I think in a few minutes we will I'll allow you to do that. Check, for example, what is in your home folder. Try to move to your folder. list the contents of the parallel computing folder that is inside the workshop. Try to do that. And let's say in the last few minutes, like a few tricks. As the command line is something that you use all the time, it's very convenient to learn a few tricks for moving into that. You don't need to type, and I never do, the commands explicitly. I use a lot things that allow me to move quickly. And one of those things is the tab completion. This works for paths, for folders, files, all that, and also for commands. So you will see that. Just typing tab, I just need to type the first 2 words or something, just a couple, 2 letters, and hit tab. If there is just one folder that fits the description that starts with those 2 letters, the command line interface will complete that for you at once. So that way you don't have to type the folder entirely. So tab completion is very, very handy. And then let's move into introduction to HPC. And that's, now I am here. And sometimes there are not unique solutions for that. So if I type just one, it will see, it first will make me a sound here on my computer, or maybe a blinking on the terminal saying, okay, I don't have a unique solution. There are several possibilities here. So if I just type one, it will offer me, after a second tab, the list of options, all the folders or files that start with one. So you can see there. And from there, you can decide, okay, I really want to use this one. So it will be, you advance a little bit, hit tab, it completes the command. So that's what I'm doing here. Another thing, there are ways of moving to folders. So you can move to this folder, introduction to HPC. And imagine that I am inside introduction HPC, but I would like to see the listing of another folder. So there are, let's say, the parallel programming folder that is on top of this. So there are ways you can see, just type the curly to identify the home folder, workshops, hands-on, which is the main folder for all the contents of the session. And inside here, I can list the parallel computing, which is right now empty, or another folder here. I think I have the scientific programming. It's empty. Probably. Okay. Okay, so inside the Spark, for example, introduction to HPC, I can list what is, this is another way, what is inside a different folder. So the 2 dots is a way to indicate, move me one folder, add, and show me for the specific folder what is inside. So there are shortcuts like this curly bracket, like the dot, like the 2 dots, that allow you to move up, down into the folders, giving a certain name to the folder, so you can navigate without having to explicitly say, like, ls, users, Franco, workshops, and scientific program. So you don't need to explicitly indicate the absolute path. This is called an absolute path. You can avoid all that. For example, replacing the first part of this with a curly tilde, like this. And it's doing exactly the same thing. So those are the relative paths. And okay, let me see. The tree, I think that I show you the tree here. A little bit of discussing the relative paths versus the full paths. And I'm wondering if I can stop here before I'm moving into the copying and creation of folders. So let's do something. I will be stopping around this point. I will give you a few minutes so you try this up to this point here. Let me see. And after we will have a 15-minute break and we return 11 a.m. For the final hour, where I will be describing the creation, movements, files, and a few tricks like symbolic links. So from the 20% that is a little bit more advanced. And with that, we will be closing the session for today. So this is probably a good milestone before we start executing things. So take the opportunity to reach this point, execute these commands, move across the file system. We will have, let's say, 5 minutes for questions. And after, we'll be relaxing for 15 minutes, drinking some water. And we start 11 a.m. Any questions to this point, let's say, related to supercomputing, the introduction to supercomputing, eventually some concept that was not clear, or the kind of things that we have discussed so far about the command line interface. By the way, everything that we are doing here, we can do it. Let me see, this is also that. We can do it here from the web interface. If you are on Thorny, you just click, you went to the Open on Demand tab, so you are working from the web interface, this web interface. You can do everything here with a terminal without a need of installing the SSH client, the mobile external, those applications of your computer. You can do exactly the same here on the web browser. So the workshops hands-on is right here. Everything that I show you here, the introduction. Another thing, in Linux, Unix, commands and folders are case sensitive. So it's not the same this to this. So and all the commands in general, the usual system commands are lowercase. So it's always expecting that. But in this case, introduction _ HPC start with an uppercase I. So you need to type it as it is. So it's very strict on those. And also, if you want, for example, here, ls-a-l, you can have multiple arguments and you can type in like that, or you can compress the arguments and using just a single dash, and all those little arguments, small arguments for ls, you can just type those, the letters for them together, and you will get the same effect. So in this case, ALL for a long description, so it was like this, and A for also showing those special folders like the 2 dots and the dot, and some hidden folders like the JIT and JIT-ignore. So folders that start with a dot will be shown when you execute ls minus al. Okay, so let me see one question. Authentication. If you are, let me see, for cloning the folder, you don't need any authentication. Let me see. Let me see. I can remove this, and I can. You need to be sure that you are on Thornyflat, the login node, and it always works. It doesn't. You don't need an user account or something. Let me see. And you are typing this command, it doesn't work for you. Let me see. Can you give me your username? I can try to type your username, and I try to become you and execute that. Okay. No, that's okay. It worked. Now you have it. Execute that. So I will be leaving for 15 minutes. I will be returning at 11 for the final hour of this. Okay. 15 minutes. If you have questions, maybe my colleagues, Daniel, Irene, Jared could answer your questions. I will be not in front of my computer, but at 11, we can answer your questions if you want. Okay? See you at 11 on top of the hour, 11. Hi. So I see one question here. So by Shali, uh, are are you able to see the folder, execute the commands on your terminal? And in the meantime, let's see. Um, well, I'm not related to the VS Code. I'm not a user of that specific program in Windows because I'm not a Windows user, and even if I could install it, but uh,
I've been looking at that. If it's a normal SSH client, I think there might be a way if you use the -x flag in the SSH, but I'm trying to confirm.
yes, let's see. I have something related to VS Code on the documentation. So let me see if I can point you to that. But and I think it's still relevant. But let me see if I have it here. Let me see. It was here in the setup where I describe a little bit the VS Code. Where I wrote it. Probably it's not here. It's right here. Oh. Yeah, I have here a few links. Let me see if those links still work. So how to access the SSH clients in Visual Studio Code. Let me see here. Use an SSH. So this is still relevant. Well, it still exists at least. And the SSH here. So if you want, you can look into those two links here are in this page. Let's see. And as far as I understand, you have like a file manager there where you can transfer files, and people do that. So transfer files back and forth between your computer and Thorny. However, there is like a trick to do that because there is not direct connection between Thorny and your computer. You need to pass by the SSH gateway. So it's a little bit trickier, but it's still possible. Some people do that, do the double jump, but it's kind of an advanced trick to do that. So you can connect that. Or inside campus, I think you can do it directly if your computer is connected to the wall or something. You can use VS Code to see and connect to them. And there is another way to do that for transferring files. There is an SFTP server, and I think we have it in our documentation, the way of transferring files that way. So there are several ways to do that. Let me see if I can find that really quickly here. in the documentation, I think it's around here. Well, this is for Globus, which is another way of transferring files. Here are the description of that. This is the preferred way when you are moving big chunks of data, so many gigabytes or multiple files, entire folders. Try to use Globus. It's much better than any of the other solutions. It transfers in parallel. It checks, double check the contents of the files once they have been transferred. So they have a lot of niceties for really transferring data. And you can transfer data between your computer and one of the clusters to the home folder, to the scratch folder, many things. And here, let me see. Okay, here there is the instructions for the transfer node for Torniflat, which is this. So this is another way of using an FTP client like this FileZilla, I think is the name of that, FileZilla, like this, where you can use it to transfer. I never personally use that. I use Globus when I need to transfer big files. Or if you want to transfer the small files, what I use is, if I am sitting in front of Open On Demand, I just go here, which is another file manager. And I can see my files, and I can, let me see if I have something like this. Let me see if I have, well, I can look into a text file or an image. So the terminal is also the file manager in Open On Demand is also convenient for it. See if I can. Yes. So there are multiple ways of doing that. So now let's move into the materials here. Let me see. Yeah. So yeah, if you want to do it from home, you need to prepare a double jump, which is trickier. This is a little bit more than beyond the level of this introduction, but it's possible. It's possible. It's also possible to jump directly into Thorny or Dolly, programming your computer to do the double jump. And there are places on our internet when they teach you how you have to do it. You have basically to edit a configure file in your for your SSH client to connect to another machine via the SSH gateway. That's basically the trick in big brushes. So let's see here. Let's return here to the workshop. And the command line interface. And we stop here around the copy, creation, and movement and removal of files and folders. All that. So that's the reason why we have a few things here. And that, let's see. Okay. So here you see we have a few files. We will be manipulating that a little bit. So some of the normal, typical things that you do on once you are on a terminal is copying files, moving files, removing files and folders. So file manipulations. So this is what I did. So now I'm located. I execute this couple of commands. So now I am positioned in this folder. I changed a few files here for working on. So the next command that you will learn, cd, ls. The next command is, for example, cp for copying files. One example here that I'm doing is copying the out card. So this file called out card. This is the output. Imagine that we are doing. This is on my area, but you have a file that you want to preserve because in the next execution that will be overwritten, and you want to preserve like a backup of that file, so it doesn't be overwrite by the next simulation or something. So we can create a backup. So this command works by describing the source and the destination. Source, the origin and destination. So the outcard, this file called outcard, will be copied into another file called outcard_bkp. And so that's something that I will be doing right now here. Okay, so now if you execute this, you see the original file plus the outcard bkp. Okay. And now, imagine that I would like to run a simulation. For the kind of simulation that I will be doing, I need a few files. So I need this file, which contains a bunch of numerical data that is, this is for material science. So this is a description, a particular description of a portion of an atom, the core of an atom. And some input files here. So some files that a scientific code uses to know under which parameters, under which conditions you want to simulate a certain thing. Most codes in the scientific domain work this way. So you prepare some input files, regardless of which area it is. Engineering, health science, biology, genomics, economy, whatever. You have some input files. And you have a code that is capable of understanding those input files, adapt the execution to them, and run the calculation for a few hours or days, and produce a result. So I will be making a copy. Instead of moving, I will be making a copy of them. But first, I will be making a folder for my execution. I will be enlarging this a little. Okay. So now I have my folder here. I will go and copy. Probably it's better to copy that. This file. So I need this one. I will need this one, both. So I can use this start. We will see that in a minute. The commodines that you can use, and I make a copy of that. And now I move into the folder. So I have the 3 files that I need for my simulation, for a particular atomic level simulation. So now once I'm there, I will execute beneath. This is an exception because we have not learned how to submit jobs, and it will be they will obscure the purpose of this lesson if I show you how you execute jobs and all that. I will do it the wrong way, which is running this on the login node, and after I will do it in the proper way, requesting a job and do it the right way. But keep in mind, what is important is the fact that I'm moving and copying files from one location to another, which is the core information that I would like you to learn at this point. So I will be executing a program for electronic structure calculations. that is called abinit. And I will be using a command that we will learn on Friday. Friday or next week? I think it's right. For accessing software. In this particular case, I'm accessing software called abinit. And I will be running a simulation. This is very short, that's why I don't feel so bad doing this. It's just a few seconds, really quick, on the login node. Again, this is not how you're supposed to run executions on the cluster. I am just showing you this because my idea is to have some files at the end and show you what is the general procedure for dealing with files, not with the execution. We will learn about the execution later. So this is how you execute for this particular code, how you execute this code using 4 cores. It will read the input, it will do some numerical operations for a few seconds, and it finishes. So that is okay. You will see here that now you have, in addition to the original files, you got some extra files. So those that has the T17O something, those are new files. Those are the output of the execution. Yeah. So the results, the answers to your question. So you are basically asking a question under some conditions. The code, if properly configured, it will run the simulation or run the model and will produce a result. And the result will be a set of files, regardless of which area you are working. The proper way to do that is like this. Let me see my I guess. Let me see if I can get it quickly. This is the proper way of doing this interactively. You have to put an extra command first, but I'm not really sure if I can get it quickly. So I will give you a few seconds to run. Otherwise, we will be doing this in the next lesson. I will. Oh yeah. Yeah, I will. So now this is the right way of doing it. So now I am in this, I execute this, and I'm no longer on this machine. And I'm on a different machine. One of the compute nodes, one of the 178 compute nodes. Now I am using the resources of one of those compute nodes. And now I can execute the same command, preparing the software, running the execution, and it will be doing exactly the same, but this time using a different computer, one of the compute nodes. That is the right way of doing this. It will take a few. Now, in the meantime, I show you there are ways of moving files or renaming files. Both things are equivalent. You use the same command for both things, for moving files to a different folder or renaming a file. So, well, this is still. Or removing files. So you use this for moving files, or you use the command rm to remove a file. If you try to remove a folder, which is one of the experiments that, let me see. I forgot that I need to do something else. Well, yeah, forget about it. If I try to, let me see, I mean, moving files, for example, T17 dot out. For example, I want to preserve that. T17 dot out dot like a backup, I can move the file, rename the file under a different name. So let me expand this a little bit. So I am renaming the file. You can also remove folders, but also only if the folder is empty. When you try to do this, it will not work because the folder is not empty. You can go here and remove everything. Nothing is now inside. And now you can remove the folder, or you can try to remove the folder. Well, if it's a directory, you have to use this. Okay, so that is some extra commands, how to remove folders or remove recursively, which is demonstrated here. So you can delete a folder with all the contents inside. And with those extra arguments, we'll do it recursively, and it will ask for every single file inside if you are really, really sure that what you are doing and you are deleting that folder on purpose, or those files on purpose. Remember, there is no trash can or something here that will save you from unintentional deletion. With some caveats. If by chance you delete something and the file was present a few days ago, there are some chances that the file has been in a snapshot, and we could eventually be able to recover it, but do not count on that. So be very careful, much more than what you typically are on Windows or Mac OS, where you have a trash being or something, and you can recover the files that you erased a few minutes ago. If you create a file a few minutes ago and you delete it, and it's not in the snapshot, there is no way to recover that file. No way. That it will not be anywhere on the system. No backups or anything that could recover that file for you. Now, if you want to exit the cluster, there is also a command for that. Well, if I leave here, it will be closing my session, yeah, because I'm using the multiplexer. So I have multiple terminals here in this case. But under normal circumstances, let's say you are here, this is that. Imagine that you are here on a terminal. If you execute the exit command, it will terminate the terminal, and you can no longer execute anything here. So that is the proper way of leaving let's see, the session here. So now, at this point, I would like you to review with you 10 commands, just 10 commands in Linux that you should know at least their name and what is the purpose of them. Even if you don't know the details, the arguments, all that, you can look into the manual page for them and figure that out on your own. But at least you need to know the name of those commands, just 10. And some of them I already showed you those, but I will go in and review those carefully here with some care, relatively quick. So the first two, echo and cat. Let me see if I can work here. Yes, okay. Okay. So echo is a command for printing on the terminal, showing on the screen some text. looks silly, but it's often used when you write the scripts. When you have a submission script and you want to type something, I am storing this execution finished. Now I am storing this and this and this and this. So those are helpful ways to mark where you are in a certain simulation. So the echo command. Also here, for example, in the introduction to HPC, you can see the content of a file, a text file, with a cat. So cat show you on the screen the content of a text file. If the file is a text file, you can see that. And most of those files here are text files. So if you are curious what this input is like that. So I am a multiplexer. So it looks like this. Cat will show you the file, the contents of that file. So that is the purpose. Echo will show you a string. Cat will show you the content of a file. Oh, you can do also small numerical operations because the shell is itself a programming language. So you can do things like this, and it's capable of computing the result. Again, it's something that you also use when you start doing scripting in Bash, in shell, and this sort of basic math operations are handy. Unfortunately, the shell is only capable of doing integer operations. So if you want to do something with real numbers, with decimals, you need to use another command, another piece of software for doing those operations. Let me see. I can do. And there is also the possibility to type a command and redirect with this symbol the output into a file. You can write a file with a certain content with this greater than. You can read this. I'm trying to go fast on this because I would like to reach at least the more challenging things, and you can read those on your own. This page will remain in place, so that I will be adding things for the next sessions, but this will remain, so you can check on this later. PWD, we already talked about this to show the current working directory here. We'll tell you the absolute path to the current location. There is one special folder that all users in our clusters have, which is the Scratch folder. This is another location. And we have basically each user has two locations, the home folder and the Scratch folder. On the home folder, you are limited to 10 gigabytes of storage. 10 gigabytes, not much. You fill that really quickly when you are doing scientific computing. On the other side, there is a Scratch space, there is a folder, where you can store, I think, up to 20 terabytes, except if we are filling too much the storage there. But you can store a lot of data there without much problem. So that is the Scratch folder, and there is this variable called Scratch that allow you to go there easily. And there you can create folders. And if you are curious, there is also this command, let's say, on the system. Oh, let me see. No. Water. In your case, it could look different, but yeah, it basically show you the amount of data that you have in gigabytes and how much you have available. Most of you will have something like 20 terabytes And there is a limit here for the home folder. What is the home folder? Is this one. I'm using 8 gigabytes and I have a quota of 10 gigabytes. Anyway, you cannot create folders at will. So only in those two places, with some exceptions, you can write files, create something. The Scratch folder and the home folder. And those are folders that are visible everywhere in the cluster. On every single compute node, you are able to see those folders, to see the content of those folders. Other locations, you are forbidden or start creating folders or files. So no, you will see a message like this. You have permission denied to create a folder directly on the root folder. So another command, mkdir, rmdir to delete folders that are empty. The commands for copying and moving, I showed you minutes ago, that you can create. There is this touch command that is also handy, that allow you to create files, empty files. So if the file exists, it will change the modification time to now. And if the file doesn't exist, it will create an empty file. This is a very cheap way of creating empty files. That for some things in scripting, like creating a lock file, we will see if we have time for those kind of things. Something that indicate that something is running. So you create an empty file just for checking to prevent a collision with some other processes or things like that. But you can copy files here, listing files. So there are a few things that you can review on your own. The things that you can do with moving, copying, and removing files. Here for removing rm, rmdir. And here is a description of all those 10 commands, what they do, and a quick example of what you can do with them. And if you're curious, you can, I noticed that we don't have the manual on Thorny for the manual pages. But over internet, if you search the manual for them, you can see the manual for those pages are everywhere on internet. And here we have an exercise to look into some files, to check what is present there. What happened when a command doesn't exist. There are a few challenges here. And there is, for example, this calendar, where you can see. So there are commands for many, many things. Okay, so exercises. You can do this. So I will try to move in the last half hour into the a little bit more specific things. Like this, another command to download things from internet, which is something that very often happens. In this case, I am showing you here that in some location, you can find a file that you need. This is for genomics, from the fruit fly, the genome of that fly. So there is a command wget for downloading files. If you have the URL of a file that you want to download, and sometimes on the browser, if you click the right click, you can see copy the link for downloading the file. So you copy the link, and you go into the terminal. Let me see, and you paste the link there. It will download the file. The alternative to this is going into your computer, deleting downloading the file, and after using Globus or some file transfer tool to move the file from your computer to the cluster. But these files, for example, those for genomics, they could be big, especially for big animals or some entities with a big genomes, trees, some bacteria. Those files are big, so there is not a point to download the file first on your computer to just transfer that. You can download the file directly to the cluster using the wget command. And now, if you see this file is compressed, some genomics codes are able to deal with the file compressed, so you don't need to uncompress the file. You can keep it like this, and the codes will do the analysis, will open and uncompress the file behind curtains, so you don't have to deal much with them. But in some other cases, what you download is something that you need to uncompress. So there are several ways of uncompressing files, depending on the extension of the file or the algorithm that was used for compressing the file. So here I am writing a description of the different tools that you can use to uncompress files. If it's a zip file, which is a very common file, a very common compression or archive, for Windows, for example, is the command unzip. If it's a RAR file, RAR, is the command unrar space, and then the name of the file. And those two here are very common in Unix systems. So you download the code, you download certain data sets or something. As those could be big or just text-based, so they have a bunch of images or something. They could be compressed to facilitate the transfer of those files. Once you get those into your computer, you can uncompress those using one of the commands here, depending on the format that that file uses. So now let's go into more things here. The wildcards. I was using that a little bit here to facilitate my work with that. And I show you here. So let's go to this one, introduction to HPC here. So I see here. So I can list everything that starts with 1. So the start is a flash wildcard that replaces whatever string I have there. So here I am looking into the contents as I'm listing, and it will replace, the shell will replace this 1 star with all valid options of files that start with 1. And it's exactly the same as doing something like this, like the 11 and the 12, well, the 10, what's coming I have, like the 1, all those folders, and I will be listing them. So of course I will be listing the contents of those folders. So this is a way of using a wildcard to skipping that. Or this, for example. So there is just one option, so it will be listing the contents of that folder. First wildcard. There is another wildcard. For example, this. Imagine that I would like to use something that starts with a number, but I don't want to use, for example, this one. So I want something that has a character there, and after the dot, and after whatever. So it will be listing all those folders here, but skipping this one. Because this wildcard here, this wildcard, only replaces one character. The star replaces whatever. The question mark will replace one character. That is another way of skipping cases. So here, for example, let me see, go here. You see here those. So you can try to see, for example, here, ls t star will list all of them. T star dot will just list elements that have 2 characters, a dot, and whatever. So it will just listing those 2 files. So wildcards, the question mark wildcard, those are more advanced. And here I have an exercise for you to go into the bin folder, which many commands are there. This is a folder where you cannot wipe, but you can see that all those commands like pwd, all those commands that I show you, most of them are right here in this folder, lsbi. So the exercise is to look into those and try to list all the commands that start with C, all the commands that start with A, all these commands that contains either of those characters. There are several ways of doing that sort of thing. Now, shortcuts. Another topic, shortcuts. I show you this shortcut you want to see. You are in the workshop, for example, and you want to see the contents of your the home folder. So this curly tilde will show you the content of the home folder. This is a shortcut to the home folder. So if you want to use relative path to that location, you can use it. The 2 dots, it will move you one folder up and show you the content of that folder. And you can combine those things. So you can move 2 folders up. So 2 dots / 2 dots is the folder up, and you see basically the same home folder, because if you move 2 folders up, 1 folder up, you move you out of the introduction HPC, another folder up, move you out of the workshop hands-on, so you are on the home folder, you will be listing all the contents of the home folder. The dot is a shortcut for the folder where I'm currently okay. So now the history. This is a listing of all the commands that you have executed before. You know that you execute something some time ago, and you don't remember exactly what you did. You can use the history and start scrolling and searching for the command that you want. There are ways for looking into the commands. For example, Control R, it will search for commands that you have executed before to look into your history for something that starts, for example, with wget, and it will show you the command, and after you get the command, you can execute it once again. Control K would delete that. So there are a few things here that you can use to accelerate, to facilitate your navigation across commands. Whatever you type here with a sharp is ignored. So that way you can put like a comment that's handy on a script, not so much on a command line execution, but on a script, it will ignore all those sharps. This command is also handy on the scripts. The sleep command, it will stop the execution, will wait for a certain number of seconds before re-executing or continuing returning the prompt back to you. So it's a way to making a pause. For some reason, you need that for going in another iteration and you are given enough time for something to complete, to finish. You use the command sleep for a certain number of seconds. The granularity is just seconds. There are some other ways of making pauses, but for seconds, sleep is the command to use. And there is this command here, for example. Let me see. Let's go to this wget, for example. And there are ways to navigate in the command line. You have this command line. There is the Control A to go to the end of the line, and Control A to go to the beginning of the line. Control, the key Control, and the letter E for the end, A for the beginning of the line. So that way you can jump if you want just to edit something at the end or just edit something at the beginning. Those are ways to use that. What else? Let me see. Okay, more advanced stuff here. Okay, let's see here. Configuring the shell. This is for you to have it on the background because we have not seen yet how to edit files. But I will show you the contents and what you can do with a couple of special files that when you have the knowledge on how to edit those files, you can start adding some tweaks to your shell that facilitate certain operations or changing the behavior of the shell a little bit. So there are two files here. Mine is somehow tweaked. But, there is this command, by the way. Probably it's in the list of 10 commands. It's a little bit like cat, the same thing. But there, bash. Oh, okay. Well, let's go first to the home folder. I'm on the home folder. So there is this command here, basher c. There is like a configuration file for your shell. You can add things there that will change the behavior of the shell a little bit. Or this other file that change also the behavior of the shell. In particular, I have here, this is a little bit tweaked. Probably you have something like this, just those first lines that will try to execute, try to source the basher C. I have here some extra stuff like this that will color me the prompt depending on which machine I am. So because I'm jumping in too many machines at this, so the coloring help me mentally to organize if I am on the login node or I am on a compute node or I am on a different machine. All that is handy. So I use this kind of coloring tweaks, and I use this way of changing the prompt in such a way that for me, it looks like this. In your case, it's probably just black and white. It doesn't have the time. Also, the time is good for me to have because when I execute a command and I can see quickly difference in time for the execution of certain commands. So I can just compare a command that took 5 minutes or something. And I can do a quick review on the timing. All those things. So those are variables and files that you can change that little by little, they will start tweaking the behavior of your shell. This is one. And here I am demonstrating, for example, how you can change the shell, the prompt here, or adding more paths to a specific environment variable for looking into executables on a different location. For example, my .local bin folder, where eventually I could have some extra commands that I'm stuck in there. So all those things. Another thing, the aliases. So probably have here, I have aliases here in a different location. Aliases are ways of having commands, shorter versions of commands that will allow me to execute things really, really quick, or skip certain executions. For example, let me see if I have. Let me demonstrate this. So, there is this command that is often used, and we will see that when we learn how to submit jobs. You use this command all the time to check which jobs are in execution in the cluster. Well, I don't want to type this all the time. So what I can do is to change with an editor. I will be using it. You will learn this later. An alias here, for example, for this command. So instead of typing the long command, I can just source this and I can execute this and I will get exactly the same as typing the long command. Another thing that you will learn when you start doing this more and more, you will notice that there are some commands that you execute very often and you would like to have some aliases, some shorter versions of those commands. So you type them quickly. You see on my bash, my aliases, I include ways to jump into a different cluster really quickly with 4 or 5 letters. And I jump into Dolly or some other machines, infrastructure machines, all that with very short versions of those commands. For that, you need to edit some text files, those bash RC, bash profile, bash aliases. And to learn that, you need to learn the text editor, which is a topic that is next to it. So this is for you to keep this in the background. You will learn how to do that. For example, I did this shortcut for listing all the files. LL is right here, and I'm using a special editor for that, the Vim editor. And here I will show you, for example, what I did. On the bash RC, you can add a shortcut to that. Another thing, in the last minutes, I will show you that there is another thing that I use personally. It's not by default for the user, but I do it very often, and is to have a shortcut on my home folder that redirects to the scratch. That way I jump to the scratch much easier than they start typing. Well, this is not bad. The $scratch, and I will be going into the scratch folder. But for me, it's easier to just type like this, or list in the folder like scratch and working with the scratch as it belongs to my home folder. But everything here is in a different location, and I have different quotas for that. So those are symbolic links. Symbolic links are like shortcuts to files or folders. And the way you create a symbolic link is right here. So ln-s for a symbolic link. There are 2 kinds of links in Unix systems. The symbolic link that is like a shortcut, and the hard link, which is like having the same file in the memory, in the storage, in 2 locations. So you are not duplicating the data. You have in 2 different locations, you can refer to the same position in the storage addressing. And the file only disappears when you delete both or all the hard links that you have created. This is a little bit more advanced. The symbolic link is probably easier or handier for most people And this is the way how you create a symbolic link. So I will be deleting my scratch. This is something that I can do. The scratch is just a symbolic link. So I can delete that with confidence. I'm not deleting my data. I'm just deleting the link and create a new symbolic link to my scratch called scratch. This is how I create, as you see here in the instructions, how you create a symbolic link. That way, all that you have to do is to type cd scratch and you see all the files in your scratch folder. Now, transferring files. For example, between two locations. So here I have this. Let me see if I have the workshops here. Well, let me see. I go to the scratch and I would like to create a workshop here. So I have a folder called workshop. And I would like to copy here CP. There are several ways of copying files. And one is the CP. So when copying this into my scratch, this is one option. Copying the file recursively will take, and those are different locations. So it's actually writing that in a different hard drive, pool of drives on the system. This is one way. And I will be deleting that. So I will be deleting the workshop. Okay. There is this command rsync, which has some niceties to that. It's like this. It's very similar to this. It's rsync. And if you use, well, if you use recursively, it will copy the files all the way. It will mention something about some special files that I create for the lessons. So you will see why it's doing that. Those are symbolic links. Or you can use this special command. That's the reason why I'm showing you this, where you can copy the files. And the next time that you execute the command, it will not retransfer all the files. It only will check if the files on the other side are somehow different from what you have on your source on this side, and only will transfer the different files. So no matter how many times I execute this, if the files on the other side are the same, it will not transfer anything. If by chance I create a file, let me see, I can use touch for creating a file here, and I execute this, it will only transfer this new file that I create. And also rsync is good when you are transferring between computers. So if you have a computer that you can address, you know the IP, you can transfer the file directly there. You can use rsync, and you can use the same tricks to transfer only the files. For example, you can transfer files from this computer to Dolly's house. This, let me see if this, see. Video is transferring the file between this cluster and the other cluster. And if I try to execute that again, well, those are, let me see, oh, okay. Probably I filled my quota on the other cluster. That's why it's not working. Let me see if I do it this way. Okay, well, we will finish. Transfer rsync, okay. And with this, we close that on top of the hour. Any questions quickly? I can entertain any questions that you could have. Otherwise, in the afternoon, for those who are interested in that, I will be showing you an introduction to Python. You'll see that here. Here. This is like an introduction to Python. I will try to present mostly examples, and I will try to leave the content of that because it's really long. I will, you can read this on your own, but I will be focusing on small programs. That is the way you really learn how to program. You don't. I always say that learning. There are some parallelisms between learning programming language and learning to drive a car. You don't learn to drive a car by reading the manual that came with the car. Same way, if you read the specifications of the language, you will not read to program. You learn to program by really looking into programs. So it means driving yourself, start making some mistakes, hopefully not too deadly. And that way you start getting an understanding and an interiorization of what it means to drive a car, or what it means to program a computer, for example, using this language, Python. So I will try to show you small examples, small cases here and there, where you can grasp the ideas. If you're interested in this, perfect. Otherwise, we'll see you on Friday for another lesson on the introduction to HPC. Okay, I see. No. Your question, no. For accessing via SSH, you don't need to be on campus. You don't need to be in the US. So this is one of the few things that you can still do out of the country. The university will block you for many things if you are out of the country. But SSH is not one of them. So you are in the other side of the world, and you can still use SSH and connect to the cluster, to the gateway, SSH gateway. And from there, you can jump into the cluster. The VPN is for some other things that you need. And in that case, some things usually not related with HPC, more administrative stuff for accessing some special machine or some special services. So you don't need VPNs for that. And for that, it doesn't work out of the United States, at least not in the official way. So there are always hacking ways to do things, but those are not official. So that's it. For the VS Code. Oh yeah. Okay, if you want to mention that for Michael for the VS Code, I know there are some people interested in the VS Code and working with that, especially those who do programming. So that could be handy. So if you want, or share with me, and I add that to the documentation, share to both documentations for this and future workshops for VS Code. So I will be happy to do that. And the page, okay, the page for the workshop, if you're asking for the workshop on this page, I will be copying this page for the workshop. It will copy here. Let me see, everyone. Is this. So the idea is that I use the dash for the contents of the workshop. I use the underscore. So there is a small difference here. So this one is for, let's say, the billboard of the workshop. And also they have also the setup instructions, all that. But the real deal is right here in the for the workshop. And here, if you go here for the Python script on the, it's right here in this in the afternoon section, if you want to see that. And again, I will add some examples, and I will be working on the Jupyter notebook. So we will be devoting some time to familiarize with the Open on Demand, with the Jupyter notebooks, how you open Jupyter notebooks on Python. So that is something that didn't mention here. So those workshops I kind of separated. If you don't attend the Python workshop, it's not a big deal. You can continue to attend the main workshop on introduction of HPC. Will not collide. It will not give you a gap or something. Those are separate things. Same thing for the next workshop, the mini workshop next week, which is in partial differential equations. Not everybody is into those sort of problems. So for those who are interested, good. Otherwise, it will not disrupt the continuity of the morning sessions that we are offering here. Okay. If that's all, thank you very much for attending today, and see you, for those of you 2 o'clock want to attend the Python session, or tomorrow 9 a.m. for the next session, which is the terminal-based editor, so how to edit files, and the modules, the software, how the Singularity containers, all the software related, the accessing software on the cluster. So all that will be tomorrow. Tomorrow, no, Friday, sorry. Okay, thank you.